All right, let's dive into electromagnetism. It's the force that powers so much of our world, from our phones to the universe itself.
You got it. And it's not just about magnets sticking to fridges. It's about understanding how electricity and magnetism are like two sides of the same coin.
Definitely more exciting than those dry textbook chapters I remember. I'm ready to unravel this connection. Where do we even start?
Well, the foundation is that electromagnetism is the study of how moving electric charges create magnetic fields.
So like electrons moving through a wire.
Exactly. As they move, they generate these invisible fields of force around them. That's the essence of magnetism.
Okay, so it's not magic in certain materials, it's all about moving particles. But how do we actually map out those magnetic fields? It seems complicated.
It can be, but we have some great tools to help us. One of them is the Biot-Savart law. It lets us calculate the magnetic field strength at any point around a conductor with current.
So if we have a wire with current flowing, this law tells us what the magnetic field looks like around it.
Precisely. It breaks down the wire into tiny segments, each contributing a small magnetic field. By considering the direction and strength of the current in each segment, we can map the overall magnetic field.
It's like taking stock of all the tiny magnetic forces. I'm picturing invisible lines of force swirling around the wire. Can we actually visualize those?
Definitely. We use magnetic field lines to represent these invisible forces. Picture a straight wire with current. The field lines form concentric circles around the wire. The further away you get, the weaker the field becomes.
Okay, I'm starting to get it. But what about the direction of those fields? Does it depend on which way the current's flowing?
Exactly. The current's direction determines that those field lines swirl clockwise or counterclockwise.
So the current is like choreographing the magnetic forces. So far we've focused on straight wires. What happens if we bend them into a loop?
Now we're talking about controlling those magnetic fields. When you bend the wire, those circular field lines interact, creating a different magnetic field pattern.
I can't picture that. Can you walk me through it?
Imagine the circular field lines merging and getting stronger inside the loop, creating a focused magnetic field there. Outside the loop, the field lines spread out, becoming weaker. It's like the loop is a lens, focusing the field.
So by shaping the wire, we can change the magnetic field. Fascinating. What if we make a coil of wire, like a solenoid?
Now you're talking about strong magnetic fields. A solenoid is a tightly wound helix of wire. Inside a solenoid, the magnetic field is very uniform and strong, almost like a tiny magnetic tunnel.
It's like stacking the fields of all those loops, creating a focused magnetic force. That must have tons of applications.
Definitely. Think of electromagnets, those powerful magnets used in scrapyards and MRI machines. They're basically solenoids with current flowing through them, creating that strong, controlled magnetic field.
Wow, mind blown. So Biot-Savart law for calculating the field, shaping wires into loops and solenoids to manipulate it. Anything else we need to know about calculating these fields?
You're in luck. There's a tool that can simplify things when there's symmetry. Ampere's circuital law.
Another law. Is it related to those circular field lines?
It is. Picture drawing a closed loop around a wire with current. Ampere's law says that the sum of the magnetic field components along that loop is proportional to the current passing through the area inside the loop.
Like measuring the total magnetic flow through that loop. And it makes calculations easier.
Yes, especially in cases with a lot of symmetry, like an infinitely long wire or a perfectly symmetrical solenoid.
Shortcuts are always welcome. We're building a magnetic toolbox with laws and techniques for understanding these forces. What else can we add?
Well, so far we've focused on magnetic fields from currents in wires. But what if individual charged particles, like electrons, move into a magnetic field? That's where it gets really interesting.
I'm listening. Do those particles experience a force?
They do, but there's a twist. The force on a charged particle in a magnetic field is always perpendicular to its velocity in the field's direction.
Wait, it's not pushing the particle along the field lines? That's strange.
Exactly. This perpendicular force makes the particle move in a curved path. Imagine an electron spiraling around a magnetic field line, changing direction but not gaining or losing speed.
It's like the magnetic field is guiding these particles. Are there real-world examples of this?
Oh, yeah. Particle accelerators, like the Large Hadron Collider, use powerful magnets to steer and accelerate particles to crazy high speeds using that same principle.
So we're talking harnessing the forces of electromagnetism to unlock the secrets of the universe. Pretty epic.
What?
What about those everyday magnets like bar magnets? How do they fit in?
Perfect timing. That leads us to magnetic dipoles. They're the tiny building blocks of magnetism, like mini bar magnets with north and south poles. And get this, current loops, the ones we talked about, can act just like magnetic dipoles.
Hold on, are you saying a loop of wire with current can act like a tiny bar magnet? How is that even possible?
It's a cool consequence of how magnetic fields interact. The swirling field around a current loop creates a north and south pole, giving it a magnetic dipole moment.
It's like making tiny magnets from scratch. Magnetic dipoles must be important for understanding all kinds of magnetic stuff, right?
You bet. It explains things like compass needles and even the Earth's magnetic field. But we'll get into that next time.
Now I'm really hooked. You've given me a whole new perspective on magnetism, and I can't wait to explore more in our next deep dive.
You're right. Magnetic dipoles are key for understanding lots of magnetic phenomena. You mentioned a big one, the Earth's magnetic field. It guides compasses and helps shield us from the sun's radiation.
Yeah, it's amazing our planet acts like this huge magnet. But I'm a bit fuzzy on how that actually works. What's happening inside the Earth to create this field?
Deep in Earth's core, there's a molten iron outer core that's constantly moving and flowing.
Molten iron, wow.
Yeah. This movement of charged particles, along with Earth's rotation, generates those electric currents. And there you have it, a magnetic field.
It's like a giant dynamo creating those magnetic forces. But I remember the Earth's magnetic poles aren't in the same spot as the geographic poles. Oh. Does that mess with compasses?
It does. That's why using a compass is a bit more complex than you might think. The difference between true north at the geographic North Pole and magnetic north, where your compass points, is called magnetic declination.
So you could be way off course if you only use a compass and ignore declination. This isn't just a fun fact, it has real implications.
Absolutely. Navigators, especially in aviation and maritime travel, need to consider magnetic declination for accurate courses.
I can see how that would be important.
And it gets even trickier. Magnetic declination isn't constant. It changes based on location and even over time.
Wait, the magnetic poles are moving? That's crazy. I guess it makes sense since the Earth's core is so dynamic, but still, wow.
It is pretty amazing. It's not just the poles drifting. The strength and orientation of Earth's field also change over time. Scientists are always watching these changes to understand how they might affect things, from navigation to our planet's protection.
Speaking of protection, isn't that connected to the auroras we see at the poles? I'm fascinated by those northern lights images. What's the link between them and Earth's magnetic field?
The auroras are a prime example of Earth's field interacting with the sun. Imagine the sun always releasing charged particles called solar wind.
Like a constant solar breeze through our solar system.
Yeah, a great way to picture it.
Yeah.
So as that solar wind approaches Earth, our magnetic field acts as a shield, deflecting most of those particles.
Like a force field.
Exactly. But some particles get trapped in the field lines and are directed toward the poles.
So Earth's magnetic field deflects most. But if you slip through at the poles, then what happens?
When those particles, mainly electrons, hit atoms and molecules in Earth's upper atmosphere, they transfer energy. That makes those atoms get excited.
Like a cosmic billiard game.
Haha, yeah. And as those excited atoms return to normal, they release energy as light, creating those auroras. The colors depend on what kind of atom is excited and how high up the collisions happen.
It's amazing those light shows are a visual representation of the invisible forces between the sun and Earth. It makes me wonder what other secrets are hidden in Earth's magnetic field.
There are always more mysteries. For instance, there's magnetic reversals. Throughout history, Earth's magnetic poles have actually flipped several times.
You mean north becomes south and south becomes north? How's that even possible?
It's fascinating, and we don't fully understand it yet. But the complex stuff happening in Earth's core can sometimes cause a complete reversal of the magnetic field. Like, Earth's dynamo flips its polarity.
So one day our compasses could point south. That's cool, but a bit scary.
Don't worry, those reversals happen over very long periods, thousands of years. Scientists are still figuring out what causes them and what it might mean for life on Earth.
It's a good reminder that our planet is always changing. So far, we've talked about fields from currents and Earth's core. But what about everyday magnets, like the ones on our fridges? What makes those materials magnetic?
That takes us to magnetic materials. Not all materials react to magnetic fields the same way. There's a whole range of magnetic behavior. It all boils down to the material's atomic structure and how those tiny atomic magnets, the magnetic moments, interact.
So we're zooming in from planets to atoms now. Can you break down the different types of magnetic materials?
Absolutely. There are three main types: diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic materials like water or copper are slightly repelled by magnetic fields. Their atomic magnets align opposite to an external field, creating a weak repulsive force.
Like they're trying to avoid the magnetic field.
Haha, yeah. Then there are paramagnetic materials like aluminum or platinum. They're weakly attracted to fields because their atomic magnets align a little with the field, but it's weak and easily disrupted by heat.
So they're not sure if they want to join the magnetic party.
Exactly. And then the superstars, ferromagnetic materials. These are what we think of as magnets, like iron, nickel, and cobalt. Their atomic magnets are very cooperative, aligning strongly with an external field, creating powerful magnets.
They're the life of the party, creating a strong magnetic force.
Right, and it's thanks to these ferromagnetic materials we have everything from fridge magnets to strong electromagnets.
It's like every material has a magnetic personality. But I've heard magnets can lose strength over time. What causes that?
That's magnetic hysteresis, which we touched on earlier. It's the tendency of a ferromagnetic material's magnetization to lag behind changes in the magnetic field.
Like magnetic inertia, resisting change.
Exactly. Think of stretching a rubber band. You need effort to stretch it, and it doesn't snap back instantly. It takes time to return to its shape. Magnetic hysteresis is similar. The material's magnetic domains, where atomic magnets are aligned, take time to align or de-align with the changing field.
Great analogy.
Yeah.
So how is this connected to magnets losing strength?
Even when we remove the external field, a ferromagnetic material might keep some of its magnetization. That's retentivity. But over time, things like heat or vibrations can mess with those magnetic domains. This weakens the magnet's strength.
It's like a magnetic memory that fades. I see how these abstract concepts affect real-world magnets. What else should we know about this magnetic memory?
One thing is that hysteresis actually causes energy loss in magnetic materials. It's like friction. Some energy is lost as heat when domains try to keep up with the changing field.
It's not just a theory, then. It has real effects. I guess engineers need to consider this when designing things like motors.
For sure. Minimizing hysteresis loss is key for making electrical devices more efficient. Materials with low hysteresis, like soft iron, are often used.
Amazing how understanding these concepts leads to better technology.
And hysteresis is just one part of magnetic materials. There's so much more to explore, from weird stuff like spin ice to using magnetic materials for data storage and even quantum computing. But that's for another deep dive.
I can't wait. This deep dive has already shown me a whole new side of magnetism. It's incredible how these invisible forces shape our world, from atoms to planets.
Yeah, this has been an awesome journey. We've talked about those magnetic fields, from currents, the Earth's magnetic field, and even all those different types of magnetic materials. But there's one thing I'm still not quite getting. Magnetic domains. What are they exactly? And how do they work with a material's overall magnetic behavior?
Great question. Magnetic domains are key for understanding how those ferromagnetic materials become magnets. So imagine a piece of iron. Inside, the atoms aren't arranged randomly. They're magnetic moments. Those tiny atomic magnets like to line up with each other. They form these little regions, and those are called magnetic domains.
So the iron is divided into these magnetic zones, each with its own magnetic orientation. But if all those domains lined up, wouldn't the whole piece of iron be a strong magnet? That's the interesting part. In a normal piece of iron, those domains are pointing in random directions. Their fields cancel each other out. That's why a plain piece of iron isn't a strong magnet on its own.
It's like a magnetic tug-of-war inside, all pulling in different directions. So nothing much happens. What happens if we try to magnetize the iron? Like by putting a strong magnet near it?
When we apply a strong external magnetic field, it's like we're adding a powerful force to that tug-of-war. The domains aligned with that external field start growing bigger, while those opposing it shrink.
So it's like some domains switch sides and join the winning team.
Exactly. As the external field gets stronger, more and more domains flip their alignment until most point in the same direction. That's when the iron becomes a strong magnet.
It's like magnetic peer pressure getting them to work together. But what happens when we take away that external field? Do they all go back to being random?
Not always. That's where magnetic hysteresis comes in, the magnetic memory we discussed. Some domains might stay aligned even without that external field, giving the iron some leftover magnetism.
So it's learned a new trick. It remembers that external field and keeps some magnetic properties. But how would we completely demagnetize it? Like, wipe its memory clean?
There are a few ways. We could apply a magnetic field in the opposite direction, making the domains flip again. Or we could heat the iron above a certain temperature called the Curie temperature.
Curie temperature. What's special about it?
At that temperature, the atoms have so much energy that they overcome those magnetic forces holding the domains together. The domains basically disappear, and the material loses its ferromagnetic properties. It becomes paramagnetic instead.
The heat melts away the magnetic order. It's amazing how temperature changes things. This shows how electromagnetism is way more than just magnets and fields. It's about connections between different parts of physics.
Absolutely. And speaking of connections, we've talked about how moving electric charges make magnetic fields, but it goes both ways. Those magnetic fields can create electric currents, too.
Wait, are you saying we can get electricity from magnetism? How does that work?
It's a fundamental principle called Faraday's law of electromagnetic induction. Basically, a changing magnetic field can induce an electromotive force, or EMF, that drives an electric current in a nearby conductor.
So if we have a wire loop and we change the magnetic field around it, we can make the electrons flow in that wire, creating an electric current.
Exactly. That changing field creates a kind of electric pressure, pushing those electrons around. That's how electric generators work. They turn mechanical energy into electrical energy.
Wow. So those giant generators and power plants are using Faraday's law to make the electricity we use every day. It all comes back to this link between electricity and magnetism.
It does, and that principle of induction goes way beyond power generation. It's the basis for so many technologies, from those transformers that control voltage and power lines to the wireless chargers we use for our phones.
It's incredible that something discovered so long ago is still shaping our world today.
Yeah.
We've gone from basic magnetic fields and forces to those intricate magnetic domains to this mind-blowing electromagnetic induction. What a ride.
It really shows the power of scientific curiosity. Understanding these fundamental laws leads to so much innovation. And who knows what else we'll discover about electromagnetism in the future.
That's what's so cool about science. There's always more to find out. Thanks for joining us for this deep dive into electromagnetism. We hope you've enjoyed learning about this invisible force that impacts so much of our world.